Good afternoon, everybody, and welcome back to ChaosWest. We are going to see a pre-recorded talk by Michael Sperber about mathematics for hackers. Michael is once was a mathematics student, but never finished his degree and is in the process of revisiting this old love of his. Deze Vortrag wird also simultan übersetzt in Deutsch. And well, enjoy.
Welcome. Well, I'm here to get you all excited about math for hackers. Now, you can have an entire hacker's life without having encountered much of mathematics. After all, this conference and this community, to a large degree, really is about finding unexpected behavior in software, such as Heartbleed. I mean, there's zillions of examples, but Heartbleed is an example where the OpenSSL API exposed secret memory through a regular API call. That was certainly unexpected. Now, you might consider this unexpected behavior to be just an inevitable part of software development because it's so complex, right? Things that you didn't expect happen due to all the complications and the complexity. On the other hand, with critical infrastructure, such as OpenSSL, you really want certain aspects of that to really run reliably, correctly. And so really, that unexpected behavior comes down to a correctness issue. And of course, that's where mathematics might come in, because mathematics deals in correctness a lot of the time in the form of proofs. Now, you can certainly apply proofs to software systems to great benefit, but of course, proofs are often tedious and a lot of work. They involve a great deal of mathematical intuition. You might not feel like that today, and you don't have to, because I will talk about something else today. I will instead talk about mathematics as a language, right? This is not a new idea. It's hundreds of years old. Here's a quote from Galileo that said, well, the world really can only be understood in terms of the language of mathematics. And, a lot of mathematics concerns itself with finding formal methods for the world around us. Now, I want to emphasize the fact that really mathematics doesn't really model the world around us directly. It really does that through the detour through our perception, right? Mathematics really is a fundamentally human construct that our mind uses to understand the world around us. And in that way, it's also a social construct because, well, we don't really need mathematics if not for communication between different people. So and that's really where, the value of mathematics for software comes in, because software also is an image, sort of our perceptions of the world around us a lot of the time, at least useful software is. So one particularly useful part of mathematics for hackers, for software construction, is, it's first of all the language of equations. And here's a couple of equations, right? X plus 2 equals 6, so it's very simple, specifies a value for x. This next equation, so x is a variable, and the next equation has two variables. It has x and y, so it says 2x squared plus 2y minus 2 equals 0. That's a quadratic equation. It might even have several solutions. And finally, there's an equation that involves a function whose definition is unknown. It just says, f of 5 plus f of 7 equals 70. Now, when it comes to functions, those are things that also exist in software. So we might conceivably use the language of equations involving functions to describe functions in our software. So we might take that equation to describe that piece of software written over on the right-hand side. And we could try to kind of work through it, right? You can see there's a function, there's a variable that's external to that function, so it goes across several invocations of it, called y, and it's initialized to 7. And maybe if we call, f of 5, x is going to be 5, to kind of try to go through it in your mind. Z is going to stash the old value of y, which is 7, and then y is going to be set to x, so it's not going to be 5. And then we multiply x with the old value of y, so we multiply 5 with 7, getting 35. So f of 5 might return 35. And with f of 7, if we then after that call f of 7, y is now 5. We stash the old value in z, so it's now 5. X is 7, and it returns 35 again. Only the product, the multiplication works in the other order, and the sum of that is 70. So you might say, that equation describes that function over there. But really, we had to go through a lot of detail and sort of tracing through the program to figure that out. And also, it only works with that initial value of y, and it only works if we call those functions from left to right. But the language of equation doesn't say anything like that we really need to respect order or something like that. Really, f of 5 in mathematics should always return the same value. Otherwise, it becomes much harder to really consistently apply the language of equations to programs. And therefore, really, so that's I guess the first hint that mathematics gives you is that you should write functions that always return the same value given the same input. But, I digress. Another aspect of the language of equations is a concept called substitution that you probably know. So imagine that first equation says, well, x equals to 7, and then there's a formula that has that variable occurring in it. And in the context of that first equation, what we can do is we can kind of plug in that equation. We can substitute every occurrence of x with the number 7 in this case, and then use that to figure out the final result of that formula. That's also something that fundamentally only works if x doesn't change over time. If your functions really return the same value every time you call them with the same input. Now, the substitution principle is not just for equations of the form where you say x is a certain number. You might also have an equation that expresses x in terms of another variable, such as the z in this case. And that first equation means, well, I can plug in 2z every time x occurs in that formula, and then use that to do further evaluation or simplification of that formula. And what's more, it also works the other way around, right? I can sort of read that equation in the second line also from right to left, so order does not matter. So that's a fundamental principle of a branch of mathematics called algebra, right? That we have variables, and that we have that substitution principle, and that we have equations. So, well, here's a well-known algebraic formula, the binomial formula, or one of them at least. And you might have learned that at high school, but today I want to look at a couple of slightly more fundamental equations, and that might have been part of your school algebra class. So I want to point out that all of these equations have names, and you might try to think of them right now, but I'll try to go through them. You might think of the names, and then I'll resolve when I'm done. So the first equation says when you multiply three numbers, it doesn't matter whether you will first multiply the first and the second one, and then the result with the third one, or whether you first multiply the second and the third one, and then multiply with the first. I'm going from right to left here. The second equation says you can swap the two arguments of a multiplication, and the third one says that you can kind of multiply out a sum, right? In the sense that when you have A times the sum of B and C, you can multiply A individually, with each of the summands there. Now, here are the names, right? The first one says, well, it doesn't matter which way we associate, the multiplication with these three numbers, so it's called associativity. The second one, well, it comes from a verb that says to swap. So it's called commutativity. And the third one is really about distributing a multiplication over an addition. So it's called distributivity. And so, these are all very valuable and useful equations, but really the most useful one is the first one, associativity. And associativity is something that works not just for plus, it also works for multiplication, for example. So really, when you talk about associativity, you don't talk about it in isolation. You have to say what operation you mean is associative or is not associative. In this case, plus or times. Moreover, associativity is something that's not restricted to numbers. So, for example, here are two Boolean equations that specify associativity for a Boolean or and. So with the or operation, you can take three Boolean values. Doesn't matter which way you or them up. You always get the same result, and the same works for the Boolean and operation. And well, these are kind of primitive values, but you can also have values that have structure. So for example, you might program with a list data structure. So you have a list with elements A1, A2, and so on until AN. And you might take two lists where the second one has elements B1, B2, BN, and you concatenate them together. I wrote this with, that funny, bow tie symbol there, concatenation. So you concatenate those two lists, and that operation that concatenates any two lists is, if you think about it, also associative. Now, what value does it have to know that an operation is associative? So here's a classic example where that's valuable. One way to think about associativity is, well, you can move the parentheses around, right? And if you can move the parentheses around, it doesn't matter where they are. And if you just and that means that you can leave them out entirely if you have sort of a chain of the same kind of operation. So imagine you have a large parallel computation that's structured in the following way. You have individual computations, A, B, C, D, and so on until Z. And they're all independent of one another. And to get the result of your overall computation, you all combine them with that operation that's written as that black rhomboid. I'm just going to say diamond from now, so the diamond operation. And so the combination works with the diamond operation, but if you know that the diamond operation is associative, it means you can sort of bunch up your ABCs any way that you like. And so, for example, you might say, well, if I've got 4 machines working on this parallel computation, I can split my individual computations into 4 bunches, combine, diamond, the first bunch, the second bunch, the third bunch, and the fourth bunch, and then combine the results of those, and I get the same results. No, it doesn't really matter if it's 5 bunches or 6 or 7, or even if it's irregular, right? And so that's the freedom that associativity gives you in distributing your computation. And this was what I just told you is a classic big data abstraction for large-scale parallel computations called MapReduce. But I really want to talk about something more fundamental today, which is how we think about the things that happen in our software. So here is an excerpt from the Java API documentation, and it draws an oval. It sort of has to do with graphics, with images. And you notice, right, the draw oval operation, it has return type void, and the documentation there talks about it in terms of pixels. Now, really, we think of an oval as a thing, right, as an object or a shape or something like that, right, as an entity in its own right. But if you look at the documentation there, you can see that draw oval doesn't create an object that corresponds to the notion our mind has of an oval, right? It just flips the colors of a bunch of pixels in some, imagined canvas that draw oval paints on. So that's very different, right? And then the notion of having a thing that's an oval is really something that our mind reconstructs from those pixels. But that gives us a very limited sort of API for dealing with images. And you can do that differently in a way that then is amenable to algebra and mathematics. And you can find that several places. One that's particularly accessible is the Racket Image TeachPack library that comes with the Racket system. So I put a download link down there, generally a great system to play with. And so this is how it works. Well, Racket is a Lisp-like language, so the syntax works a bit different from Java or C in that when you call a function, the parentheses go, around the function call and the arguments are separated by white space rather than commas. So first thing is you call a function called circle, you pass it 3 arguments, 50, solid, and red, and it returns a red circle, well, as you might imagine. But really, I want you to understand that it doesn't, flip pixels or something like that. It really returns an object representing the circle, and it's only the Dr. Racket API that then displays that object as an actual picture that we can view. But it could also, do something else with that picture. Save it to a file, send it to somebody over the network or something like that. First function returns a circle. Second function, there's also a square function that returns a square. You can see I can put outline instead of solid to say that I want just the outline of a square, or there's a blue star at the bottom returned by the star function. So these 3 functions are kind of primitive in the way that they create images out of thin air from a bunch of numbers and strings. And you Here's another such function called right triangle that creates a triangle out of thin air. Now, there's three more operations here that don't create something out of thin air. So there's the rotate function, for example. It takes an image, an existing image has to exist before you call rotate, and rotates it, in this case by 10 degrees, just a little bit. And then there's two other functions, flip vertical, which flips an image vertically, and flip horizontal, which flips it horizontally. So it creates a mirror image, if you will. Now, these two functions, they transform an image in some way. And what's important to understand is an image object goes in and they return an image object also. And that image object that's returned, you can pass it to other operations. So for example, that's what happens here. You can, for example, you can rotate that triangle, again, as we did on the slide before, and you can pass that result. You can stick it into flip vertical to then flip the rotated image. Now, what you see here is particular examples. So what happens to the triangle when you first rotate and then flip, but some of these things can be generalized to general equations that hold for all images. So here's two very simple examples. The first one says, well, if I flip an image and I flip it again, I get the same image out again, right? And that, I think, hopefully plays to your visual imagination or intuition. The second equation says, well, if you flip horizontally and then vertically, or you do it the other way around, you first flip vertically and then horizontally, you get the same result. And again, that should conform to your visual intuition. So those are two general equations that characterize how images work and how image construction works. And, we can get some particularly useful equations from these three operations that are on this slide here. Now, what they do is they don't just take one image and output one image the way that rotate and the flips do, but they take two images each and return one image that results from combining them. So the first function, beside, takes two images and sticks them together horizontally, gives you the resulting image. Above, puts them above each other, gives you the result. And overlay puts them on top of each other. And these are operations, they have the same form as plus or list concatenation or multiplication or and in the sense that, or takes two booleans, returns a boolean. Plus takes two numbers, returns a number. Beside takes two images, returns an image. Same thing for above and overlay. And whenever you have that, you have a function that takes two things, returns one thing, you can think about associativity, and you should. And in fact, these functions, if you kind of work, again, through your visual intuition, you can figure out that beside, above, and overlay are all associative operations. So with overlay, for example, it should be especially intuitive in that if you have three images on top of each other, it should not matter whether you first kind of staple the top ones together and then the bottom one to the bottom, or whether you first staple together the bottom two and then put the top one on top. In each case, you have, layers in the same sequence. Now, what can you do with, what can you do knowing that you have an associative operation? We already talked about parallelization. Generally, you can do optimizations based on for example, some of the other equations. For example, the equation that says, flip horizontally twice doesn't do anything. You can use that to optimize, right? When you see somebody doing a flip twice, you just throw out those operations. You don't have to compute the actual flip. You can also imagine computations where you can cache intermediate results in the same way that you kind of process that parallel computation in a tree shape. And it gives you great flexibility in that caching and recombining the cache values. So you can just use that for performance. You could also turn those equations into what's called property-based testing, right? You could stick in random values for the variables and test whether the equations are actually fulfilled, and that might help you debug or ensure the correctness of your library. And finally, if you really need something to be correct, then you could provide formal proofs giving you added assurance using a technique called induction, because you combine two things into a thing and you kind of have to walk that construction backwards. But again, this talk is not really concerned with proofs that much. But again, I mentioned that earlier, I really want to talk about the modeling aspect that this mathematical way of thinking about it suggests, right? Again, remember sort of the Java draw oval function that just flips the color of a bunch of pixels. And, here's the picture, but really we view this picture, our mind views this picture as, a bunch of concentric circles, and each circle is a thing in its own right. Now, I don't know what's intuitive to you, but apparently, it was intuitive to some people to create that first function, draw oval. And that mathematical intuition really tells you, really make pictures, make images into objects, and then create abstractions based upon them. So, we can use mathematics to kind of, create equations after the fact. But really, mathematics gives us great suggestions as what the library, what the API should look like in the first place. That, I often see people doing something else, so that intuition might have something to do with that mathematical understanding. So let me talk a little bit more about that language of mathematics, now that we've figured out the importance of associativity or equations in general. So, people working in algebra, they always talk about structures that have three parts, and or have three pieces, right? One piece is a mathematical set, so just a collection of a bunch of things, of objects. Then they have operations on those sets, and then they have equations involving those operations. So on the right-hand side, you can see what we know already. So we have some set M, could be anything, could be booleans, could be numbers, could be images. And then you have an operation, diamond, that combines two of those M's into one M. Well, here's a little bit funny notation, right? With that cross there, what it says is there's two inputs, right? Cross, cross, cross for each input. So the diamond operation has one M as an input, another M as an input, and then there's the arrow, and that says that there's also an M as the output. And then finally, there's that associativity equation that we've already seen quite a few times today. And those three things packaged up together, the set and the operation on that set, in this case, just a single operation, and the equations, in this case, associativity, this is all called a semigroup, right? And there are other algebraic structure that we'll see. Now, this translates directly to programming. Your set M in mathematics might just be a type in your program. And these semigroups, they occur in lots of places. So with all of those things that we've already seen with associativity, you could just kind of shorten your language and say all of those things are semigroups. So for example, at the top, it says, well, if you take the mathematical set of real numbers, that's what, that funny R, that hollow R that you see, the real numbers. With the plus operation, it takes two numbers from the R set and produces one number. Of course, has associativity, therefore it's a semigroup. Lists with concatenation fulfill the associativity equation, therefore they form a semigroup. And for example, the overlay operation from the images, just as beside and above do, has that same shape, right? Combines two images into one image and fulfills associativity. Therefore, images and overlay form a semigroup. Now, a semigroup is not the only algebraic structure, but it's a fairly humble one. It can't do a whole lot, and therefore, kind of mathematicians build up from them. They take a simple algebraic structure and they add more operations or something else to it. So, for example, the next step up from a semigroup is something called a monoid. So, you take a semigroup and you add something. And I'll try to explain what that is. So again, you have a set, you have a binary operation, that diamond operation. And you also say that in that set M, there has to be a special element, right? And you have to know what it is. And that element is called bottom. That's what that line says, the upside down T, that's what I call it, bottom. And it also has to be part of that set M. And now, as usual, because every monoid is a semigroup, the associativity equation holds. And the bottom line explains about the identity element, about the bottom element, where it says, well, if you use the diamond operator to combine A with the identity, or identity with A, you get back A. In German, you often use the word neutral element. So it's really, it's neutral with respect to the binary operation that you have in your semigroup. And hopefully that appeals to your intuition as it does to mine. If you take an algebra class at the university level, you might learn about more involved algebraic structures such as groups and rings and fields. And every time you go a step up, right, a monoid is a semigroup plus the neutral element. A group is a monoid with even more more operations and more equations. A ring even involves a second, a ring involves another operation and more laws. Same thing for a field. So, you just add a bunch of stuff as you go up the ladder. But for hacking, really for computing, for writing software, the two most important ones from that stack here are semigroup and monoid. You don't really have to worry about the rest unless you really write mathematically inclined software that involves those algebraic instructions. So we've seen a bunch of semigroups. Have we seen a bunch of monoids? Yeah, well, essentially all the semigroups that we've already seen are also monoids. So for example, the plus operation on the numbers, right? 0 is the identity there. You add 0 to a number, you get back that same number. With multiplication, well, you multiply a number by 1, you get back that same number. You have a list. You concatenate it with the empty list. Doesn't matter whether it's left or right. Well, sure enough, you get the same list. Now, the bottom three examples might look a little bit funny because they suggest that there is an identity for those operations, but they all are the empty image, so they're invisible. And so that points that out to you. And monoids, I can't really overemphasize this. Monoids are everywhere around us, right? So, now, software engineer asked me a while ago and said, well, your mathematical structure is all good and well, but what about really concrete, software things? We do shopping carts. How could you possibly use mathematical structure for a shopping cart? But of course, a shopping cart, you might have a shopping cart associated with your account at some shop, right? But on another day, you might go shopping, you forget to log into your account, but you can usually still, fill a shopping cart. Now, once you check out that shopping cart to buy the stuff in it, it will usually ask you to log in. Now, there's two shopping carts, one inside your account and the one that you just filled. They have to be combined into one. And really, it's worthwhile to think about what properties that combination operation should have. But there's many other examples from monoids. I have some concrete examples from applications that I've worked on. Famous paper in functional programming, for example, is about financial contracts. Sure enough, they form a monoid. Recently, I talked to a company that makes configurable flower bouquets. So you might combine two sets of flowers into one to form a bouquet. All kinds of things. Monoids really are everywhere around us. So much that, my friend Carl Elliott has elevated this to a general design principle. Whenever you write software for a particular domain, you should look for mathematical algebraic structure. And because monoids are so common, one thing that you can always try is look for binary operation on your objects, check if the associative law holds, look for an identity. And if you don't find that binary operation, okay, but if it's not associative, that's maybe a sign that you should try to make it associative. Doesn't always work, but frequently does, and usually gives you some improvement in the process. Same thing for identity. If there isn't one, you might make one up, trusting that you might need it later. Carl calls this a Tau check. Something that I really like is whether the software model that you're creating aligns with mathematics, and that means the deeper structure of the universe that humanity has discovered in the hundreds of years that were there before computing. Monoids are also useful in differentiation from things that are not monoids. So for example, the maximum operation that gives you the bigger of two numbers does not form a monoid. It gives you a semigroup, it's associative, but there's no identity, right? Thinking about it, you might think, well, but can't I take like minus infinity or something like that? But of course, that's not a real number, but it maybe gives you a hint as to how you could complete that structure if you really need a monoid. And I'll get back to that in a second. But first, I want to talk about a general principle in that, you can't it's not just discovering sort of monoids in the domain objects around you. You can also construct monoids systematically. Specifically, you can create larger monoids out of smaller ones. So this is probably the most complicated slide that I have, so don't worry, it'll be over in a second. But we'll try to go through it line by line. So imagine you have two monoids. And the first one is called M1, the second one is called M2, and each has their own diamond combination operation. The first one is called diamond 1, the second one is called diamond 2. First one takes two M1s, gives you back an M1. The second one takes two M2s, gives you back an M2. Now, using those two monoids, you can create a larger monoid by taking pairs of elements from M1 and M2. That's what that funny cross means. It means it's something called the Cartesian product. So it forms out of two sets, it forms the set of pairs where there's one from each of those two sets in there. And in order to make that a monoid, we have to define a binary operation. I'm just going to call it a diamond. And you can see the diamond is defined in such a way that one pair out of M1 and M2 goes in, another pair out of M1 and M2 goes in, and it returns another pair out of M1 and M2. And the way it's defined is you take two pairs and you combine the first elements from both pairs using the M1 monad and the diamond 1 operation. And you combine the second elements of both pairs using the diamond operation from the M2 monoid. And sure enough, that gives you an operation that's associative. I didn't put that on the slide, but it also gives you an identity with a pair that consists of the individual identities from M1 and M2. That works. Also, sometimes you have a semigroup lying around, but you really need a monoid. A semigroup that's not a monoid, but you really need a monoid. Here's a little construction that will build a monoid from a semigroup. So again, we start with a set. We start with a binary operation on that set called diamond. And then we create another set that I call M bottom. Again, that funny upside down T that you see there. And we create it by adding artificially one new element to it, right? It can't be in there before. And then we define a new operation, diamond bottom, that operates on that set. And we just define it in such a way that if either side of that operation is the identity, the bottom element, we just have it return the other side. So, bottom, diamond bottom, bottom returns you A, and the same thing the other way around. And whenever, that operation is called on two things that are not bottom, we just call the original operation. And sure enough, that gives you a monoid, even if the thing before, the M before, was just a semigroup. And you might have seen that construction in programming. So for example, the Java library has something called an optional. And that is exactly that. And again, when you're defining abstractions like that, the mathematical notion and the mathematical equations can provide a guide as to how that API should behave if it's supposed to be reasonable. If you still bear with me and have a little bit of patience left, here's another concept, it's a little bit more abstract, called the homomorphism that's useful in thinking about APIs, at least APIs that combine in this way via something like a monoid. So look at the first equation. It says, well, if you take an overlay of two images A and B, maybe more like this, right, and you rotate it, that is the same as taking one image, rotating it, taking another image, rotating it, and slapping them together after the fact. And this is what's called, so what that means is really rotate here is what's called an homomorphism. It can kind of slip inside the overlay operation. Or another way to talk about it is commutes, or it can trade places with the overlay operation. And that on the left-hand side of the equation, the rotate is outside and the overlay is inside. And on the other side of the equation, it's exactly the other way around. With the next equation there, flip vertical of beside, right? And then the idea is, well, you flip one, and then do beside. That's certainly eminently reasonable, but if you think about it, it might depend on the alignment that you choose for your images as you put them side to side, right? You might decide to align them by the top half like this, and then, well, you might come to the conclusion that that equation does not hold. So, but again, it provides a guide. It probably should hold. You should design the beside operation in such a way that it works. Now, the equation at the bottom really does not work, right? Oops, there it is. But if you have 5 minutes after this talk, or even now, you might think about an equation that's very similar to that one that does hold and that gives you some insight. So that's also a useful notion when you're designing APIs. Here's another useful notion in that, well, with images, there's the visual aspect, right? That we perceive images by looking at a certain pair of coordinates and perceiving a certain color. And, that color we might represent it by a value, and that value might come from different types. And that gives you different notions of images. So, for example, an image of bools, well, so each coordinate can only be on or off or black and white, so it gives you a black and white picture. The next one, where there's just a number there, it might give you some notion of grayscale. Or you could, of course, then, as in the bottom two examples, you could stick RGB triples in there to give you arbitrary colors, or even an alpha channel or something like that. So when you have a type such as image that has a parameter, very frequently you can add a little bit of structure, what's called a map operation that you might have seen. Not going to worry about the details there, but you might get a structure called a functor. The word functor comes from a particularly abstract branch of algebra called category theory, but even the mathematicians sometimes call that abstract nonsense. But despite the term, it really is something that's very useful and very insightful into the structure. It gives you a lot of insight into the structure of things. And category theory frequently describes relationships between things through diagrams that are quite beautiful. So here's a characterization of the idea of a monoid. You don't have to understand that diagram, but maybe, after this and after you've mastered monoids for a while, you'll have a look at category theory and enjoy it. You get more complicated diagrams such as this one and more involved abstractions, such as, I mentioned functor. There's also the infamous monad, and these are things that are practical, eminently practical for creating higher order and generally higher level abstractions. Again, not for this talk. That's a different talk. But I hope I've instilled in you the sense that mathematics, at least this kind of simple mathematics, is useful. If you felt that it hasn't been simple, that it's been hard, I want to point out that, well, it might be hard to understand everything that's been on the slides on this talk, but it's not due to the fact that it's complicated, right? There's not a lot of moving parts or something like that. But it is abstract, and the human mind, needs some time and finds it difficult to deal with abstraction. And therefore, you might also, if you're interested in this stuff, you might give your mind some time to get adjusted to those mathematical concepts, and maybe look at it again in a couple weeks. Just have a brief look. Maybe look for a monoid or just a binary operation. Look for associativity, and by that stuff will become more familiar and commonplace to you, and you'll find it easier to deal with it. And once that happens, I think you'll find that very satisfying. So that's pretty much it. If you want to read up some more detail on this, I've put in 4 references that are linked from the slides that you can hopefully download from somewhere. But you can also just kind of search for those titles and you'll find those papers. So first one is a paper by Brent Jorge that really takes that idea of using monoids to structure an image library to the limit. So that's just a great paper. Then there's a book by Sandy McGuire on algebra-driven design, who he applies that idea to different practical settings. Connell Elliott gave a great foundational type talk on something called denotational design. So that's a video, also as a paper, but I really recommend you look at the video. The classic paper that introduced this notion of dealing with images by combining them is by Peter Henderson, something called functional geometry. And I hope you'll enjoy looking at that stuff as much as I will. And I hope you enjoy the Congress. I hope to see you around. Have a good time. Bye.
So thank you for this interesting talk, Michael. And there are a few questions from the internet already. And for those who haven't asked questions yet, if you use the hashtag RC3CWTV on either Twitter, Mastodon, or the proper IRC channel, we can still include them in this Q&A. And the first question I would like you to ask you, Michael, is maybe a strange one, but you mentioned this concept of homomorphisms of the monoids. And I was wondering whether we could do the reverse around. Could you use these mathematics to visualize APIs?
That's an excellent question. Let me think about it for a moment. So with a monoid, So yeah, so the answer is, first of all, is yes. So with a monoid, one way to think about a monoid is not just this abstract thing that's going on, right? But since any value in the monoid, you can kind of be built up by this operation that's sitting in the monoid. You could also just represent a monoid not just by some abstraction, but you can build what's called a free structure. And that is tree structured, and that you could visualize. So that's one half of the answer. And on the last slide, I had a reference. The very first reference on a paper by Brent Jorge shows how that works, and it's generally a paper on visualization. So that would be one half of the answer. The other half is that I remember one industrial project that I've worked on where people wanted. So there was kind of a complicated data flow problem. And the requirement of the customer was, well, people want to assemble a configuration for a scheduling problem in semiconductor fabrication, if you will. And they said, well, we just want a bunch of boxes and arrows, and people should be able to arrange that visually to specify a configuration. And we ended up looking for the right formalism to do that. In fact, there is one in category theory. I mean, category theory generally is diagrams. But there is a concept in category theory which just happened to fit, and we found it by going from the customer requirement to the mathematics, and that gave us a naturally and very pleasant and actually mathematically precise visualization form for that. So I argue it's a great tool to think about visualization. Hope that helps a little bit.
Okay, so we can finally look forward to this kind of neuromancer-like landscapes while hacking.
It feels like that sometimes, yeah.
Yes. Another question was from a viewer who had never seen such sexy algebra in their life, whether you're willing to submit a proposal next year to go to more in-depth continuation talk.
Sure. Very happy to.
That's a short. That's a short answer to a relatively long.
Can't say you haven't been warned, but I'll try.
Yeah, and also it needs to be accepted, the content thing, obviously. Another question that is about something you said you wouldn't talk about, and that is about formal verification of algorithms.
Yeah.
But nonetheless, it might be useful for the audience to know if there's an informal verification of algorithms, what avenues you would suggest to people, especially people without much of a formal background in mathematics, to start looking at, as it places for further learning for that topic.
Yes, that's an excellent question. So I think one place that I'd start with, and I think there have been talks about this at earlier iterations of the Congress that I'm sure you can find. There's in fact, there's a new, if you will, family of programming languages that are based on strong types called dependent types, and they're very expressive, and they allow you to express mathematical properties. Now, in the old days, we would write down a mathematical property of a program that we wanted to have, and then we would use, if things are good, we would use a proof assistant to find the proof, and that would be a very cumbersome, process that you would have to do. Now, with this new family of programming languages, Idris and Agda are two prominent examples. What you can do is you can give a type and you can push a button, essentially. It's not quite so easy, but there's actually IDE support where you can push a couple of buttons and it will generate a program that has that type. And that program is guaranteed to be correct, right? Because with the combination of the type and the program itself, there is the proof right there sitting there. And that, at least for simpler things, takes away a lot of the burden, that at least the burden of getting into this kind of tool. It's still kind of intricate work to put together more complicated proofs, but to get into that medium, it's just great fun and it's very satisfying activity, and you don't have that impression that you sometimes have with proof assistants that you're kind of fiddling in the dark with a screwdriver. So if it's a concrete place that you're looking for, I would recommend looking at a programming language called Idris, and maybe look at some of the Congress talks that we've had about it in the past.
Yeah, having been to at least one of those Congress talks, I also would ask a follow-up question to that. Does the new typing capabilities that, for example, Rust provides, rise to this level that you mentioned with Idris and other languages, or is that not advanced enough for that yet?
So I'm not an expert on Rust. I haven't seen IDE support on that level. I'm pretty sure the type. I mean, Rust has a type system that has a specific kind of expressive capability that allows you to express memory safety, right? And then because your type correct program, if you're not using the unsafe features, is guaranteed, is kind of proven to be correct to adhere to those memory safety criteria. But I have not seen the general expressivity that languages like Idris gives you in Rust. Maybe there's a way to do it, but I'm reasonably confident it's not as practical and not as easy to get into.
Yeah, and also it's way off topic since you said you wouldn't be talking about this anyway in by now. So we're sort of hearing this.
That's fine.
The other one of the other questions is, will you be around in the 2D world sometime to talk directly to people from the audience?
Yeah, sure. We'll do that right after the talk. Maybe after a little lunch break.
And what nickname will you be using? Where will you be hanging out?
My Twitter handle, which was also the beginning, called Spurpson.
We have this 2D RC3 world, this kind of online adventure thing where people visiting are walking around with their avatars but you haven't been there yet, I take it from your.
No, I have been there. I'm just saying my avatar there has the same name as my Twitter handle, which was.
I'm sorry for interrupting you.
It's called Spurpson.
Okay.
Spurper was not available anymore.
Apologies.
So I'll be there. I'll be there.
Yes. And I think this. There's another question. And there's something like a Turing machine have been constructed with the mathematics of 2,000 years ago.
So I got Turing machine and I got mathematics as of 2,000 years ago, but I lost that.
Could something like a Turing machine be constructed with the mathematics of 2,000 years ago? This may be a bit of a speculative question.
I don't see anything that wasn't there. I don't see why not. Yeah. I'm not 100% sure what exactly the mathematics of 2,000 years ago was, right? My basic knowledge goes back a couple of hundred years. But the basic mechanism of Turing machine is very simple. It's not my preferred mechanism to talk about mathematics and hacking, but sure, why not?
And the I think the question is, she says, I'm teaching Haskell in teaching.
Well, that's a great question. It kind of goes, I'm doing a workshop later on teaching programming. I think teaching programming using Haskell is a terrible idea. Obviously, you all know I'm a big fan of functional programming. I actually do a lot of Haskell in my daily life, and I've given talks using and on Haskell in the past. But Haskell is a programming language coming out of a research community and used for professional programming. If you really want to do an effective introduction to programming, you're well off using specialized programming languages for learning. That's what I'm going to advocate later today at 4 p.m. Middle European time.
Okay, thank you all. And this concludes this session. Thank you for being here.
Thank you. Thanks for having me.